Thank you for staying for the last hour of today. So at least relative to my plan, I'm a little bit behind. So just as a feel of the audience, would you like me to go faster? Who would be happy that I go a little bit faster? Who would be happy that I go a little bit slower than I've went? Okay, I'm just perfect, I see. Okay, yeah. Okay, so I'm going to go faster a little bit, and you stop me. And because I didn't, I'm okay. So these protocols, these primary backup protocols, they basically have three, they're built of three parts. So the first part is kind of this normal case protocol, where the primary is allowed to commit messages, and essentially if the primary is non-faulty, then decisions will be made. The second part is this way to basically replace the primary. And so first we have to trigger this replacement. And the second thing is we have to actually run this view change protocol, which we discussed, which basically makes sure that if the previous primary decided something but was faulty, and somehow this decision didn't arrive to everybody, then this new primary will take the same value as the old primary. So here's kind of the normal case protocol for omission failure. It has just three phases, again, very simple. So the first phase, the primary sends its value to everybody. So it has, the message has two elements. One is what is the value it's sending, X. And it's also saying, I'm sending this in view V. So remember, view is kind of this counter that says, who is currently ruling this regime. And so that's the simple thing that happens. And the thing that you, again, trivially need to do is if you hear the primary, you acknowledge this message from the primary. And so if you hear the primary, then you send this acknowledgement. And in this protocol, we'll just send acknowledgement to everybody, all the other parties. And you'll do this as long as you're also in view V. So if you somehow move to a higher view, then you ignore this primary. And maybe in kind of the partial synchrony model, we'll care about this because maybe some people might drift to V+1 earlier than other people that still stay in V. And finally, we'll make this simple decision rule. And the simple decision rule is we'll wait for n-f messages of acknowledgements. And if we receive n-f acknowledgement messages, we will decide the value X. Okay, so the protocol is very, very simple, right? The first round, primary sends everybody, here's what I'm proposing. In the second round, everybody sends an acknowledgement to everybody else in the room. And in the third round, we just count the number of acknowledgements. And if you see n-f acknowledgements, so in our case, this is f+1 acknowledgements, then you decide the value, and that's it. You never change your mind. You don't terminate. You might need to continue to run, but you decided, right? You're not going to change your mind for X. So this is very simple. And so the next thing we're going to do is we're going to replace the primary. And so there are many ways to replace the primary. In fact, in many practical systems, you actually want to keep the same primary for multiple different consensus rounds. Or sometimes you want to rotate the primary in a random way. But for now, we'll just do a very, very simple approach where we'll wait for, let's say, 4 rounds. And after 4 rounds, we'll replace primary 3 with primary 4. And then again, we'll wait 4 rounds, and we'll replace primary 4 by primary 5, and so on. This is kind of the way we're going to build the trigger. And finally, what we need to do is we need to build a view change protocol. So what is the view change protocol? It's basically a way for us to make sure that if there was a decision, we will learn about it. And so really the risk here is that you're a new primary, and you have to make sure that you're consistent with the old primary, right? The old primary had some rules, and you want to make sure that you're not deciding on different rules than this old primary and break safety. So again, sometimes you have to adopt a value that is not your value, but is your previous primary's value. And I promised you some math, so here is where the quorum intersection actually happens. So indeed, it's the case that if somebody has a decision, it's only if it has n-f acknowledgements, right? And so if there's n-f acknowledgements, it means that if I'm a new primary and I read from n-f parties, then I will see one of these acknowledgements. Because in particular, even if there's n-f, which is f+1 here, acknowledgements that I hear, I might decide. And if the new primary reads from f plus 1, then this f plus 1 will intersect the f plus 1 of my acknowledgements by at least one member. And this one member will tell me about the acknowledgement. It won't tell me about the decision. It will tell me about the acknowledgement. And you know, this is safe because of quorum intersection. And it's live because I can always wait for n minus f parties. Even if there are f omission failures, if the new primary is non-faulty, then it's okay to wait for n minus f, right? Because even if the faulty don't send any message, I will still receive n minus f. Okay, so again, this is kind of reminding you what the normal case is. And so here is, so in particular, you can just see that in the normal case, we wait for n minus f acknowledgements in order to decide. That's kind of the simple rule for decision. So here's what the new primary does. So if we don't know who the new primary is, it can announce itself. But in our model, we just know if the old primary was 5, then now the new primary is going to be 6. So there's no need to announce. And what the replica does is it sends the maximal propose it ever heard. So it says my maximal propose is the value x, and it was in x prime, and it was in view v prime. And what the replica does here is it looks at all the different proposes it heard, and it sends the one that has the maximal view v prime. Okay, so this is the only kind of trick that the replica has to do. A replica saw many acknowledgements in many different views. Let's say we're now, I'm the primary of view 10, and I ask one of you, you're a replica, and you might have seen different acknowledgements, different proposes, in different previous views. There might be views where you did not see any propose because maybe that previous primary was faulty and omission failure. Or maybe you are omission failure, and so you did not see all the proposes. But what you do is you take all the proposes of all the different views, and you take the one which has the maximal view that you saw, and you send that to the primary. Okay? And so that's the simple thing that you do, and if you didn't see anything, you just said, well, I didn't see any propose. And what does the primary do? So this is kind of the view change phase. The primary waits for n minus f responses, so these types of responses. And what does the primary do? It wants to make sure that if there was a decision, it will not miss that decision. So among all the different proposes it hears, which proposal should it take? Any guess? Who said? Maximum, yeah, maximum one, right. So this is, again, the next thing that you need to do is you need to choose the maximal view number. And if all of them are empty, then you can choose your own value. So a new primary can't just use its own value. It uses its own value if all of them basically say, I haven't heard any propose. But if some of the previous replicas saw a propose, then what you as a primary need to do is choose the maximum one, the one with the maximum view. So this is the only trick of these primary backup protocols, that the replica chooses the maximum view to send to the primary, and the primary of all the messages it receives chooses the one with the maximum view. So here is the whole protocol in one slide. So this is essentially let's say, a version of Paxos or Rafts, view stamp replication. There's a bunch of these different protocols. This is a protocol that's widely used in industry. Obviously, it's wrapped around a lot of more complicated things. But what you're seeing here is basically the core of the consensus protocol of all these protocols that reaches decisions against an omission failure model. It has a normal case. The normal case has 3 phases. The primary sends a message. Everybody responds with an acknowledgement. And then if you see n minus f acknowledgements, you decide. And then we just wait 4 rounds. And after 4 rounds, we replace the primary with another primary. Okay? And the new primary, what it does is it waits to hear from n minus f of the other replicas. In particular, each replica says, here's the highest proposal I've ever heard. And what the primary does is it chooses the highest one, or 0, and it uses this value when it sends a propose. So the way it chooses this value x is by this rule over here. So this was kind of, again, this is the core of Paxos. If you understand this, you understand many consensus protocols that are used both in practice, and they're going to be the base of the next phase of protocols that we're going to use. So at least is the protocol clear? Good. So we're going to briefly talk about two things we need to prove. So, I mean, we need to prove validity, but obviously, validity seems kind of simple here. But what we need to show is safety and liveness. And again, the core challenge will be safety. What we'll be worried about is what happens if a primary decides on some value, and maybe this primary, this primary causes some replica to decide on a value, but maybe due to omission failures and so on, this is the only replica that decided, right? So there's maybe not everybody has decided, and now we want to make sure that no later leader will choose a different value. This is kind of the core thing that we need to show, and so this is a safety proof. And all these proofs have a very similar structure. You can prove them either by induction or by kind of a counterexample. So we'll do kind of the positive version. And we look at the first view that some replica decides, and let's say it decides on a value x. So the protocol is running multiple views. Maybe on the first view everybody decides, that's great, but maybe it takes 30 views until somebody decides. And what we want to make sure is that all later decisions will be on the same value x. So that's what we want to show. That it is not the case that somebody decides x and somebody decides x prime. So obviously, in the same view, it must be x because we don't have a Byzantine adversary. So we're going to have to deal with that in the next proof. But what we're going to show is that any primary that adopts a value in a view v that's larger than v star, right? V star is the one where somebody first decided, must adopt the value of x. Okay, so basically any primary that comes when after v star, when it does a view change, it will have to choose the value x. And the way you could prove this is by basically show that there is a set of f+1 guardians. So these are basically parties that maintain the fact, in a distributed way, they maintain the information that x was potentially committed. So what do these guardians have? So the property of these guardians is that their maximal propose is on a value that has x. So they have some maximal propose, which is at least v star, and it's on value x. It might increase over time. And the other property is that anybody outside of G, if it has an equal or higher maximal propose than any member in G, then it also must be on this value x. Okay? So there's at least f+1 parties that are locked on this value x, and everybody outside, either they have a lower proposed value, or if they have a higher view proposed, then it's on the same value x. And why is this true? So it's true because whenever we make a decision, let's say on v star, then if somebody decides, then there are at least f+1 that sent a acknowledgement to you. If they sent an acknowledgement, it basically means that their maximal propose is on x and on v star. Right? So this is kind of the induction step for v star. And you can do the same induction on every phase after v. And one thing to notice here is that this type of argument basically looked at views. So the induction was on views. We did not use any notion of time here. So this type of safety property holds even if the system is completely asynchronous. So even if messages arrive in a completely unordered way. So this is kind of the sketch of the safety proof. We're going to do the same thing later in the Byzantine model and maybe in more detail. Yeah, so, and termination, well, it's kind of easy. We just wait for a non-faulty replica, right? Because a faulty replica as a primary might not send any message, and so will make no progress. But even if we have a faulty primary, then after 4 rounds, we're going to replace this primary. And maybe after t+1 replacements, f+1 replacements, we will eventually have a non-faulty primary. And this non-faulty primary will basically send a message to everybody, and everybody will send an acknowledgement. I mean, all the non-faulty ones, and so everybody will have n-f acknowledgements and will commit. And so here in this argument, we did use synchrony because the fact that when a non-faulty primary will cause termination, or will cause everybody to decide, we use the fact that these messages indeed will arrive in 4 rounds before we replace this primary with the next primary. So here we kind of use the fact that we're in a synchronous model in order to prove that we get termination when there's a non-faulty primary. So note here that We get termination once we have the first non-faulty primary. So in particular, if the first primary is non-faulty, then we get termination in a constant number of rounds. So that's quite nice. But in the worst case, we actually have to wait for t+1 view changes before replacing the primary. Any questions on the termination and safety arguments?
Not sure about what it is about, but why 4? Why 4 rounds?
Oh, I don't know. Yeah, maybe I could have used just 3, right, or 2. So here, all you need to wait is that this thing happens. So this is maybe 2 rounds. So yeah, this could be optimized maybe for 2. Or you have to wait. You basically want to wait. Say no message is being sent here. You don't want to replace the leader too quickly. So the simple version is just wait, let's say 3 rounds. So this takes 2 rounds, right? So you send, and then you send acknowledgement. So maybe it could be optimized for 3. More questions? Yeah.
Assume synchrony, then you don't need view changes, is it true?
This protocol needs view change. Yeah, because I mean, you still are worried in the omission case that maybe only one replica decides, and now you want to make sure that the new replica doesn't make a mistake. Right? So the trigger becomes more complicated in partial synchrony. This is what I would say. Good. So yeah, so this is kind of a very successful model of this primary backup in partial synchrony, where again, this is this partial synchrony where you have asynchrony at the beginning, and then there is some unknown point in time where there is a stabilization, and then the system becomes synchronous. And so if we have a round-robin protocol, then what will happen is that in asynchrony, we'll basically just replace the primaries round robin, and eventually, once the system stabilizes in this global civilization time, then we will do another maybe f+1 rounds until we get one non-faulty primary. So this is, again, a very successful model, and this goes back to the question asked earlier. So it gives you kind of safety in asynchrony and liveness in synchrony. And it's very successful as a protocol in industry, and it's also a gateway for asynchronous protocols. So we'll show how you can actually take this and lift this to asynchronous protocols. Okay, so finally we get to Byzantine adversaries. And so the question is, maybe we can do the same thing. We can reach agreement in synchrony or in partial synchrony using the same number of parties, 2f+1. We saw that even for omission, we can't do 2f. There's a lower bound. So how about doing it for 2f+1? Can we do that? Who's going to put money on a yes? On a no? Ah, you had the lower bounds. Yeah, okay. So, okay. So let's do this lower bound. So in partial synchrony, we have this very simple split-brain approach attack. So here there are 3 parties, A, B, and C, and we want to show that if one party is Byzantine, remember now it's not the omission model, now it's the Byzantine model. If a party is Byzantine, it can actually send different messages to different people. It can behave arbitrarily, right? And so now what this Byzantine party B will do, it'll create a split brain. On the right side, it will talk to C and say it has input 1. And on the left side, it will talk to A and say it has input 0. And we'll use partial synchrony so that there's going to be this red line is basically going to say that all messages between A and C are blocked. Right? They will not arrive due to asynchrony. And so in this model, again, what you can show is that there's kind of another world where only A and B are correct, and this third world where C and B are correct. But really what you can see here is that even if you had cryptography, even if you had signatures and so on, you could not circumvent this split brain attack from basically causing A to decide 0 and C to decide 1. Right? So this is kind of a very simple split brain lower bound, very powerful. Even if you had a PKI, you could not solve a Byzantine agreement in less than a third, in more than a third, if the adversary controls more than a third. In synchrony, we have a slightly weaker type of lower bound, which says the same thing, that you cannot solve a Byzantine agreement for n parties if one of them is Byzantine. And this is this Fisher-Lynch-Merritt from 85 lower bound. And basically, what you do is you build 6 different parties, and you connect. So you see here, party A is connected to B and C, and here party B is connected to C and A, and party A is connected to C and B. And so the way you should think about this is to look at each edge. So if you look at an edge, it defines 2 honest parties. Let's say we'll look at this top edge. It defines these 2 honest parties, A and B, that have an input of 1. And it also defines an adversary. So the adversary controls all 4 of these parties, and it basically simulates in his mind 4 honest parties. Okay? So basically, this is world number 1, where you have 2 honest parties, and all these 4 are simulated by the adversary. So as you can see, in this world, due to validity, A and B have to decide 1, right? Because all the honest parties have the same value 1, and so they have to decide 1. And in the same way, if you look at this world where A and B start with 0, and the adversary controls all these 4, then in this world, A and B have to decide 0. And then what you can show is that in every one of these edges, basically, let's say this node here, it runs in 2 different worlds. It runs in one world where C and B are honest, and the other world where C and A are honest. In both these worlds, the view of party C is exactly the same. It's essentially the same execution. So party C is seeing exactly the same view in the world where B is honest and all these 4 are malicious, and in the world where A is honest with C and these 4 are malicious. So it cannot distinguish between these 2 edges. And then you can move from one edge to the other, and since in the top you have to decide 1, and the bottom you have to decide 0, you get, again, a safety violation. And so the core point of this lower bound, well, it's showing you that even if you do not have partial synchrony, you just have synchrony, you still have, you cannot solve a Byzantine agreement for n equals 3, or basically anytime the adversary controls more than 1/3 of the parties. But you do need to have the adversary have the ability to control or to simulate in his head more than one party. So in particular, if there's a PKI, then maybe I cannot simulate in my head these parties. Or if I have to simulate proof of work, then maybe I have just proof of work of power 1, and now I'm required to have proof of work of 4 times my ability, to simulate 4 parties. So this is kind of a lower bound that is weaker in some sense, but is stronger because it also works in synchrony. There's questions about these 2 lower bounds. So if we need to solve Byzantine agreement, we need to solve it with 1 failure. We can't do it with 3, so we can do it with 4 parties. Right? That's kind of what we could do. And so what I hoped in my mind is that after you've all solved the 2-round protocol for omission failure, you will also solve this 2-round protocol for 4 parties. So I'm not going to let you do it today because we have not enough time. But if you like to add this to the homework, then this is in addition to solving for 3 parties. This is, I think, one more trick that you need to apply. Try to work for 4 parties and a Byzantine adversary, right? So this Byzantine adversary, now we can cheat, right? So it's not just omission, it can actually say 0 to one person and 1 to the other person, and maybe in the next round it can, send something incorrect and so on. Here you don't have to solve for uniform consensus. So people who did not like this notion of uniform safety, here you can really look at kind of the clean problem of Byzantine agreement. So tomorrow morning we will have a competition for people solving it in 2 rounds. So this is, let's change it, let's make it a homework. Okay, so we're going to look at the Byzantine model, and there's 4 parties, because for 3 you can't we have a lower bound, right? So if you can do 3, it's probably because you have a model where the adversary cannot simulate, and it's in the synchronous model. Yeah, so basically, we're going to take the previous Paxos protocol that we've seen and lift it up to a Byzantine adversary. We're going to augment it to be resilient to a Byzantine adversary. And so there are two things that we want to block the Byzantine adversary from doing. The first, we want to block it from saying different things to different people. So previously, when the adversary was Omission, it could send a message, maybe not to everybody, but at least it couldn't lie about the message. It couldn't say 0 to one person and 1 to the other person. And so we want to block that. The other thing we want to make sure is that the adversary actually does the view change. Because currently, the view change was a key aspect of safety. And now what if the new primary is malicious and it sees all these proposals, but it doesn't choose the maximum, it chooses some other value. So we want to force the adversary to do a correct view change. These are the two things we want to worry about. So first of all, we want to make sure that the adversary is not inventing a value. And we also want to make sure it's not choosing a non-maximal value. So these are the two things we want to work against. And so what we're going to do is to solve the first problem, we're going to add one more phase to deal with non-equivocation. And to solve the second problem, we're going to add one more phase and this idea that instead of forcing the adversary, the new replica, to send the highest propose, we will basically make sure that the guardians, the one that you've seen in the safety proof, they will not accept a proposal from a primary that gives you a low view. So basically, they will reject the primary. So we're going to use this idea of locking on values to prevent the primary from sending old or stale values. Okay, so here's kind of the Strawman protocol. So again, this is this two-round. You send a value, the replica accepts it, sends marks that it's locked, and sends the lock value to everybody. So I'm just replacing the name acknowledgement with this word lock. I didn't change anything else. I gather n minus f different lock values, and then I decide. So the nice thing here is that at least in one round, you can't decide on different values. Because I'm waiting for n minus f different lock values, and because I'm just sending one lock message, I'm not going to send two different ones, then you can't have n minus f values for one value and n minus f for the other. The problem here is that, we want to somehow keep the history of this decision. So if this decision happened, we want to make sure that the new primary hears about it. Previously, the way we did this is by looking at the proposals. So here, we basically said that if you receive a proposal, then you mark yourself as locked. The problem here is that it could be that there are many different replicas that have different lock values. So a faulty primary can basically cause somebody to decide in this protocol. And not only that, it can have different replicas have different lock values. And now when a new honest primary tries to recover things, it will not be able to recover what is the correct value. It will see multiple values and it will not know which value to choose. So you could imagine saying, let's choose the majority value and so on. It will not help you. So the adversary can actually cause the majority value to not be the majority value of the lock, to not be the one that's being decided upon. Benny, we have half an hour or 15 minutes? Half an hour, okay. So really what we want to make sure is that not only are the decisions the same, but all the lock values are the same. So the way we're going to do this is basically add one more phase in order to make sure that the lock values received are the same. And so this is done by this trick of non-equivocation. We want to transform a Byzantine sender into an Omission sender. This is kind of a reduction from Byzantine to Omission. Very simple. Again, number of failures is less than a third. The solution is just we send a message. Everybody sends an echo for the first send that you see. And then if you see n minus f echoes, then you accept the message from the dealer. So it's just adding this message, adding this n minus f gathering of echoes. Okay? And so by doing this, we've basically forced the Byzantine adversary to become omission. The only thing it can do is send one message. Maybe not everybody receives this one message, but it cannot be the case that one person sees 1 and the other person accepts the message 0. Why is that the case? Yeah, so it's some sort of there's actually there's 2f+1 honest and f, so there's even more than a majority. So really what we want to prove is that it can't be that one person accepts value and the other person accepts value prime. And let's just prove this by simple contradiction. So let's assume that you see n minus f echoes of value v, and maybe I see n minus f other echoes of value prime. Okay, so now we're going to again use this fact that any n minus f, two n minus f sets intersect by at least f+1. And so in this f+1, there's at least one non-faulty, right? So there's f Byzantine. They can say value to one person and value prime to the other person, but one person here has to be faulty. This one person will not say two different values because it just sends for the first value it hears. And so this is kind of the contradiction. And so this is kind of the reason why there will not be two different values. Okay, so it's a very simple one-round protocol that forces you to become omission failure from Byzantine failure. Right? This is clear? Good. Yeah. So here's how we we augment our protocol. So the primary sends, and now we will add this echoing, and only after this echoing we will send this lock. So the lock is the old acknowledgement. And now we basically solve the problem that the locks themselves are the same value. So it can't be that in the same view, two different honest replicas see two different locks, because to see a lock you have to wait for n minus f echoes, and so this is exactly this non-equivocation. So we're forcing the primary to basically send a message that if I see a lock here, everybody has the same consistent lock. So that's exactly the same thing that we had in the omission failure model. And now what we're worried about is how to force the primary to choose the highest lock. So remember, in the view change, we actually have to learn all the locks and choose the one that has the highest view. Yeah, so this is kind of a reminder. This is how our view change protocol looked like. You send the maximal propose, and then you choose the maximal out of that. And so, can we force the new primary to adopt the maximum value? So you could do this essentially. If you have cryptographic tools, you would basically kind of give maybe essentially a zero knowledge proof that you've chosen the maximum among all the messages that you've received. There's also ways to do this in an information theoretic way, and this is kind of Castro's thesis. But we're going to take a different path, which is just to prove that this value that the primary is using now is a value that some old primary has already used. So I'm not going to prove to you that it's the maximum one. I'm just going to prove to you that it's some value that was sent in a previous view. Yeah, so this is kind of, if you know these modern protocol, Tendermint, hot stuff, and so on, this is their view change variant, which is kind of slightly different than this PBFT variant. But we could have done both of them. Today I'm going to show you this hot stuff version of view change. And so in this paradigm, once the primary proves it's using a real value, a value that was sent by a previous primary, we still need to ignore this if a replica has already seen a value from a higher view. So if I've seen a value from a higher view, and the new primary sends me a message from a lower view, I'm going to ignore this message. So this is kind of the main idea of view change. Questions about this? Good. So yeah, and so the high-level idea for safety will be that once there is a commitment, there's going to be f+1 honest replicas that are locked, and essentially locked on the highest view number. And so if a primary tries to come in with a different lower view number, so it doesn't choose the maximum, then these f+1 replicas will block it. And the reason they will block it is because this new primary has to receive n minus f acknowledgements, but it will not because there's at least f+1 honest that will block it. So that is the main core trick of view change in this Tendermint hot stuff paradigm. So before I go on, if there's any questions about that. Good. So I will go over this a little bit in more detail. Yeah, so what is our goal now? Our goal now is to solve this first task, which is to make sure that the primary, when it's sending a value, is actually adopting a value that was sent in a previous view, okay, and not just inventing some value. So if we had signatures, it would be very simple. I could just give you a message signed by the previous primary. And that would be a proof that things work. But this is a winter school for information theory, so we have to use information theoretic techniques. And so we will. And the way we'll do this is by basically saying that we don't want just non-equivocations. Remember, we managed to force the primary to not send two different values. We want a stronger property. And this property is that if I accept a primary message, then everybody else will weakly accept it, and eventually, maybe one round later, will really accept it. So we want to have this stronger property that if I accept a message, then everybody also accepts this message. And so this is, again, this well-known techniques. In the asynchronous model, this is reliable broadcast. And in the synchronous model, this is kind of a gradecast. This is Mikaeli and Feldman's gradecast, and this is Bracha's reliable broadcast. And so I'm going to show you a version that does reliable broadcast because I'm also going to try to do partial synchrony and eventually synchrony. Yeah, so here is kind of a protocol where the goal is that the primary not just sends a value and it cannot send two different messages, but also has this property that if I accept a message, then everybody will eventually accept this message. And as you know, we're doing information theory, and I told you that there's no math other than just quorum intersection. So the only thing I can do is add one more round. Okay? So I'm going to add one more round because that's the only power that I have. Yeah, so we're going to just use echo twice. So the first round of echo is just non-equivocation. And then if I see n minus f echo once, then what am I going to do? Well, I'm going to send echo 2. Right? So this is kind of a new echo. And I'm going to do the same thing here, which is if I see n minus f echo 2s, then I accept this message. So until now, I really did something boring because I've just showed you, 7 times the same thing. So there's one more twist here, this one more twist. And this is like, what happens if I see a weaker threshold of echo 2s? So if I see f+1 echo 2s, I still will weakly accept it and I send echo 2 to everybody. Okay, so this is this one more thing that we are doing now. We're reacting to one more threshold. So in addition to the n minus f threshold, we're reacting to the f+1 threshold. So there's a high threshold where I accept a message, and a lower threshold where I weakly accept and send this echo to. Was there a question? Okay. Well, here, where? In the f+1? So if I would accept only here, then it's not clear that everybody would accept. Because if I see f+1, maybe everybody sees just 1. So we will prove in a second, right now, these 3 properties. So the first one is that all the accepted values are the same. That's non-equivocation. That we proved already. Yeah, you have a question? Oh, that's a bug. Ignore it. Sorry. So some cryptography creeped into the information theoretic. Yeah, but everything here is information theoretic. But to your question, here is kind of here is the property that I think will not work if you just use the f+1 threshold. So it's very simple. It just says that if a non-faulty accepts, then all non-faulty will at least weakly accept. So why is that true? So when do I accept? I accept when I see n minus f echo 2s. when do I weakly accept? When I see f plus 1 echo 2s. So why is it always the case that if some honest party accepts, everybody at least weakly accepts? Yeah, so out of the n minus f that I heard, at least f of them, at most f of them are malicious, right? So n minus f of them are non-faulty. So n minus 2f are non-faulty, and n minus 2f is at least f plus 1, right? So that means that everybody will hear at least f plus 1 echo 2s. Okay? So basically, this is kind of, if I see 2f plus 1, everybody sees at least f plus 1. That's kind of the intuition here. And moreover, if we're thinking about kind of an asynchronous model, then not only will we weakly accept, but since we actually are sending echo 2, what will happen? All non-faulty will send echo 2. Right? And if all non-faulty send echo 2, what will happen? Everybody will strongly accept. Right? So eventually, everybody will accept. Right? This is kind of the last claim. All right, so this is kind of the main trick in information theoretic Byzantine fault-tolerant protocols is to run 2 rounds of these all-to-all, not just one, and to have this 2 thresholds, n minus f and f plus 1. This is reliable broadcast. This is a very important primitive. And what this allows us to do, it essentially allows us to simulate a signature, because it says that if I receive this message, then I'm sure that eventually everybody will receive this message. Right? And you can't kind of send a different message because of this property 0, non-equivocation. So this is kind of an information theoretic way to obtain some properties needed, and in particular needed for our protocol. So here is kind of the protocol in one round, so in one slide. So on the right side, what you're seeing is here you're seeing the view change. Here you're seeing this auxiliary, what you do with f plus 1 echo 2s. And here you're seeing the main protocol. So the main protocol, basically what we're doing is, remember, the primary sends a message. And now we have this echo 1 and echo 2. And the thresholds here are n minus f. So you send a message, and if it's the first message, you send this echo 1 to everybody. If you see n minus f of it, you send echo 2. If you see n minus f of that, then you accept the primary's message. So that's essentially the same as in the omission model as just receiving a propose. So if you reach this step and you see n minus f echo 2s, it's exactly the same as if in the omission model you receive a propose. But now you're also guaranteed that everybody will eventually see this same message that you saw. This is the reliable broadcast. And so now you can lock your value and you can send this value. And after everybody sees n minus f acknowledgements or locks, they can decide. So what we did not, so this is kind of the main protocol. This is the auxiliary thing that we're doing to add echo 2s. And this is the view change. And here's how the view change is different. So the replica still sends the highest lock and value it knows about. So it sends the maximal value. Yes? No, this is n minus f for echo 2. This is this causes you, this n minus f is the non-equivocation. Remember, that's what we did. Yeah. So here is kind of the new thing that happens. So the primary previously just received these locks from all the different replicas and chose the maximum one. Now what an honest primary is supposed to do is when it receives a lock, this lock might be a fake lock. It might be a lock that never existed. So I basically wait to receive a signature that this lock arrived, and this is basically n minus f echo 2s, that this is a true message that has been sent previously in the system. So I wait for the reliable broadcast to work, and I wait for n minus f such locks. Why is it okay to wait for that? Because, well, all the honest parties will send an honest lock. And so and so this non-faulty primary will choose the value with the highest lock. Questions about this protocol? So what is missing here is still the fact that the primary, when it sends a message, it has to choose a value that was sent in some older view, because we will verify, or we can verify. So in this phase, we're not even verifying this thing. So what we're going to do is verifying it, and this is the whole protocol. So now you're seeing a Byzantine primary backup protocol that has kind of all the ingredients. So in particular, there are two important things that we want to do here. First of all, the primary, when it sends a value in view v, it also sends us this u. U is the view of the value of this value that this primary chose, right? So the primary can choose either to send its own value, or it can choose to adopt an old value. If it chooses to adopt an old value, it must say, here is the view I chose to adopt, and u is this number. And so what do you do as a replica? Well, you do two things that are new. First, you have some lock, and you make sure that the view that the replica is sending you is at least as big as what you've seen. So this is making sure, for safety, that you as a replica will not accept messages from a lower view number. And the second thing you're making sure is that this u and value are indeed correct, are indeed sent. And here you just wait for n minus f echo 2s. So this is the two new tests that you make, and you just, all the remaining protocol stays exactly the same. So so what we're going to do now is go over the safety argument. And the safety argument is going to be, again, very similar to the omission failure safety argument, where we're going to look at the first view where any non-faulty replica decides. Let's say this is view v star, and the value is x. And what we'd like to do is prove that any replica for any later view must adopt the same value as the value that was decided in v star. So it's exactly the same argument. And yeah, there's kind of a base case here that we need to make sure, and this base case is due to non-equivocation. So due to the non-equivocation, it can't be that there's both in the same view, a primary managed to send two different values. And then the induction argument basically requires the same type of argument, saying that there is a core of f+1 non-faulty that are locked with a value of at least v star and the same value as the one that was decided. And the reason this is true is, again, you can look at the base case. So in the base case, if somebody made a decision, it means it received n minus f locks. It means that at least n minus 2f of those were from honest parties, and these n minus 2f are exactly the core of f+1. So they will be the ones that are locked. They're preventing new primaries from making bad decisions. And so you can, again, do this kind of standard induction argument, showing that in every view, this has to remain true because you have this core that is locked on high values. Liveness, again, it's the same thing. We're going to assume that there's a non-faulty primary that's elected, and the system is synchronous. And when the system is synchronous, then you hear locks from all non-faulty. And since you hear locks from all non-faulty, you can choose the maximum view from all those. And when you choose the maximum from all of those, this is a typo. Not a typo. So basically, since you choose the maximum, then all the non-faulty primaries will have this property that what you send them, the value u, will be larger than their lock, because you've already heard from all the non-faulty and you chose the maximum. So obviously this property will hold. Yeah, so one last twist is we would like to obtain liveness in asynchrony. And so this is maybe slightly harder, because in asynchrony, it might be that a non-faulty primary will miss some locks, because it can only wait for n minus f responses. So it might not hear from a honest replica. and so it might not choose the highest locked value. And so what is the solution? Yeah, you add one more round, right? So after seeing n minus f echo 2, basically what we want to make sure is that if somebody has a lock, then there are a lot of people that will know it has a lock. So this lock will not go hidden. And so basically we can solve this hidden locking problem by adding one more round before locking. So this is kind of this final protocol. So this is essentially an information theoretic analog of hot stuff. And it has all the properties that we said earlier. It's just that now when I receive this echo, I don't set the lock, I set a key, and then I send this key. And if I have n minus f keys, then I set my lock. So now the property is that there's an honest party that has a lock, and there is a lot of people that have a key. And so when the primary does a view change, this view change will see this lock because it will see a lot of the key members. So what are the nice things about this protocol? So this protocol works for partial synchrony. You can wait until you have a honest primary, and when you have an honest primary, then if the system is synchronous, then you can commit. And what we're going to show tomorrow morning, after we hear from the finalists that can solve two-round Byzantine agreement, is how to transform this protocol into a constant expected round protocol. So this protocol, is deterministic. There is no randomness here. And so it obviously has to take f plus 1 rounds. It actually has to take order f plus 1 rounds because there's like a lot of rounds here of sending. But what we'd like to do is basically choose a random leader. And not only that, we like to choose a random leader in a way that an adaptive adversary cannot attack. So if we just naively choose a random leader, then an adaptive adversary can shoot down this primary. And so what we'll do tomorrow is basically show how we can use randomization to augment this protocol to get a constant expected number of rounds. The way we will implement this is by modifying this protocol to allow multiple primaries to run in parallel. That's one thing. And have an oblivious leader election protocol. This oblivious leader election protocol will use some version of verifiable secret sharing that we've seen in the first day. Verifiable secret sharing needs broadcasts. So what we're going to do is replace the broadcast there with simpler primitives, in particular tradecast, and show how we can still build a reasonable leader election protocol using these primitives. So that's the plan for tomorrow morning. Thank you.